class. Okay, now we're going to look at a device called a cyclotron. So kind of drew it here, need to explain what this is. But we have these two objects that are called Ds. And they're called Ds. If you look at this one on the right, it looks like the letter D. What they actually are these, kind of like if you put them together, you'd have like a cylinder. Basically, so you just have a nice cylinder. And you cut it in half. So you separate it. So there's like a plate on top, plate on bottom, wrapped around. And they're made out of metal. Okay, so those are called Ds. So the inside is hollow. You can move around. There's no wall at the edge. And say we place a positive, it would work just as well with negative charges. Let's say we place a positive charge in the gap between these two Ds. And because they're metal, we can charge them up. So let's say we give the one on the left a positive charge and the one on the right a negative charge. And so that's going to create an electric field going from the positive charge to the negative charge. And this positively charged particle is going to accelerate until it enters the region, until it gets inside the D. Now, inside the D, these X's represent a magnetic field that exists inside the D. So what's going to happen so it's going to accelerate across this gap. So it's only affected significantly by the electric field. I mean, gravity is always a factor, but again, these are very tiny particles, like protons or electrons. So they're going to move so fast that gravity is not going to significantly affect their motion. And so in the gap, the only thing affecting their motion is the electric field. So it doesn't matter how we place it here, say at rest, it's going to accelerate, acquire some speed when it enters the D, and then it's not going to be under the influence of the electric field, but it will be under the influence of a magnetic field once it enters the D. And to remember when we talked about a mass spectrometer, kind of the same thing. We're going to enter a region with a magnetic field into the page. It's a positive charge. So remember, fingers in the direction of velocity, curl towards the field. There's initially going to be an upward force. Remember that force is always perpendicular to the velocity. So as it starts curving upwards, the force keeps changing direction, so they're always perpendicular. And we have circular motion. So let's draw what this is going to look like. It's going to accelerate until it enters the D, and then it's going to go through this hemisphere motion. Now this gap between them is kind of small. Let's just analyze this part from when it enters the D in one end and then comes out the other end. So we can start with Newton's second law. F equals ma. So the force we know is a magnetic force. That's the only thing that's significant on the particle inside the D. So that now the velocity is like along the board. It's in the plane of the board. The magnetic field is always perpendicular. So theta is always 90 degrees. Sine of theta is always going to be 1. So we have E, V, B. There's no sine of theta to worry about. On the right side, it's in circular motion. So if you remember, the acceleration for uniform circular motion, or circular motion in general, the centripetal component of that is v squared over r. We can cross off one of these v's. Let's actually solve for the radius, kind of off to the side. So the radius is going to be mv over eb. So the radius of this path inside the D, that's the mass of the particle. Let's say a proton, it's going to depend on the velocity. It's proportional to the velocity of the particle. And again, E and B are constants. So that's one important result, that the radius is proportional to the velocity. Like if we had a stronger electric field, it would be moving faster, it would go through a bigger circle. But I want to come back to this equation. Let's multiply both sides by r. So we have EBR equals mv. I also want to look at how long it's going to take to get from here to here. How long is it going to take to travel through one of these d's? And we can just use, it's moving at a constant speed, so distance is speed times time. Now the distance is half a circle, that'd be pi times the radius, that's v times however long it takes to get halfway around the circle. And so we can solve for the velocity. So the velocity is pi r over t. Let's plug that in. Okay, and finally let's solve for time. So we're going to have two important results. And if we just solve for time, here's what we get. M pi r divided by EBR. Now, m is the mass of the particle, pi is just a constant, these are fixed. Something very important happens here, these r's cancel out. So t, I'm going to put the pi in front. What we find is that the time is constant. So it doesn't matter how fast the particle's moving. If it's moving faster, it's going to go in a circle with a bigger radius, so it's going to cover a bigger distance. And, bigger circle takes more time to cover, but it's moving faster. And they just work out so that the time is independent of how fast the particle is moving. Okay, so far we're almost there to describing a cyclotron. So say we place a particle in here, it's going to accelerate, it's going to enter this d with a certain velocity, and then it's just going to swing around through this half circle, and now it's like it's going to hit a wall, because now the electric field is opposing it. This is a positive particle, so when it enters the gap between the two d's, now the electric field's in the way. It's going to cause it to slow down and stop, right in the middle. If it was here at rest, it's going to stop right in the middle. So that's not very useful. So what if in the time it took this particle to loop around, what if we flipped the polarity? So that, initially we had this one positive, this one negative. That'll churn all these arrows around. I'm not going to keep redrawing them. I'll just draw it like this. See, these arrows are flipping back and forth as well. Now, it might seem like this would be kind of a difficult thing to pull off in practice because you have to time it just right. But that's why this is such a critical result. The time does not depend on how fast it's moving. And we can even calculate the time it takes to complete half a cycle. We just plug in the mass of, say, a proton, the charge of a proton, and whatever magnetic field we're using, and that would be the time it takes. That's how often we'd want to flip the polarity. And if you remember last lecture, we're just talking about alternating current. So if we hook this up to an alternating power supply that the current can distribute these positive and negative charges on the D's, we can pick a frequency so that everything is timed just right. And so what's going to happen is we place it here, it's going to accelerate through this gap, and then move at a constant speed around here. And then when it gets to this gap, it's going to, instead of slowing down, because we reverse the direction, it's going to speed up. So now it's going to reach this D on the left going faster, and it's going to go through a bigger circle. And again, the speed inside is constant, But every time it gets to a gap, the electric field is oriented properly, so it's going to accelerate this charge, and it's going to keep on accelerating. And the bigger we build this device, the faster we can get this thing going. And again, the faster the velocity, the bigger the radius you need. So you can start it out with the object even at rest, and it's going to keep spinning around until it acquires a very high speed. And then at the end, say we just direct it outwards at the very end, and we have a beam of very energetic, high-speed particles. And the bigger you make this, the faster you can get these particles moving. So this device is called a cyclotron, and this was one of the earliest particle accelerators. So now we've got these incredibly enormous things like Fermilab or the LHC in Europe. These extremely powerful particle accelerators. This is kind of like a first generation particle accelerator. Got a really cool picture of it. You can see the D's. It's kind of a lot going on there. You can see it's a pretty large device. And you can actually see a beam of particles coming out. These are protons, I believe. Oh no, that's a beam of electrons, but either way. It works either way, protons or electrons. Now, you might think, well, why don't you just keep making it bigger and speeding these particles up even more? The problem is this breaks down at some point. What we did here breaks down. Because we're sticking with what we call classical physics.